Hey everybody, Dr. D here. This is what I call my periodic table video. This is designed to get you familiar with the periodic table and to be watched at the beginning of the course and be used this knowledge throughout the semester. So this is our video for Chem 1030D periodic table, basically. Your textbook for this course isn't really a chemistry textbook and therefore does not have, great chemistry background. It's an environmental science textbook. So I make this as a way to give you some of that information. So throughout the semester, whether it be quizzes or worksheets, there might be information in this video that is helpful. I want you to just get familiar with basics of the periodic table, nothing to memorize, no intricate details. So let's share my screen here. And of course, this is just our home page right now. Let's drag this periodic table over here and look at this. Okay, so I'm going to expand this completely. All right, so this is our periodic table now. Now, periodic tables are arranged in order of increasing atomic number, which is the number at the top. You see, this is telling you that. That is the number of protons in the nucleus of the element, okay? And that number is synonymous with the element that it's corresponding to. So that means, hydrogen always has one atomic number, one proton. No exceptions to that, always. And the periodic table moves across. 1, 2, and it comes back over here. 3, 4, 5, 6, 7, 8, 9, 10. So if I say 6 protons, that's synonymous with saying carbon. And if I say carbon, that's synonymous with saying 6 protons. So that's the signature of an element, its number of protons. Now, you should know that the nucleus, and this is discussed in chapter 2 in your book, in my slides too, is that the nucleus contains the protons and the neutrons. That's where most of the mass of the nucleus is. And outside the nucleus are the electrons. Now, the neutron number can vary for an element. And what you see down here, so let's look at carbon. You see that number at the bottom below the carbon, 12.01. That's known as the average atomic mass. That's because of things that we call isotopes. Isotopes are atoms of the same element that have different numbers of neutrons. So, for instance, carbon, the major isotope of carbon is carbon 12. Okay? What that means is since it has 6 protons, 12 minus 6 is 6. That means it has 6 neutrons. That's the total number, the mass number. That's not on the periodic table to look for that. Okay? It might be close to this number, but that's not the same number. And that's not on the periodic table. But there are different isotopes of carbon. There's carbon 14, which means since it always has 6 protons, it has 8 neutrons. So the atoms of an element, their neutrons can vary, but the protons are always the same. 6 protons is what makes it carbon, but the number of neutrons can vary. Okay? So what that number at the bottom is the average mass of all the isotopes. Okay? So you can actually tell from looking at this one is 12 is going to be the major isotope because it's closest to 12. That doesn't always work, but for carbon it does. So we got increasing atomic number. And since these things weigh, the mass is going to increase as we go across. We also have the numbers down here go from here down to here, and then back up and finish, and then come over here and come down here. This is really done for most of anything for convenience. Because imagine putting these 2 whole rows right here and squeezing them in here. You would not be able to fit this on an 8.5 by 11 sheet. This also groups them for particular reasons also. But honestly, the first reason it was done was really for convenience. So you look at different names too. These are my alkali metals and alkaline earth metals, groups 1 and 2. And then they go across 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18. Group 2 is the alkaline earth metals. Halogens are over here, 17, and the noble gases are 18. There's other ones, but those are ones that you might have learned in the past. The symbols in the middle. So this is platinum, which happens to be 78 down here. These are called the transition metals, these blue ones in the middle. These are different names you don't have to worry about down here. Lanthanide and actinide, they're often called the intertransition metals. So transition metals here, increasing atomic number. Now, The number of electrons in a given atom, let's go back to carbon, is the same as the number of protons because matter is neutral. That means the number of electrons which are negatively charged and the number of protons which are positively charged must be the same. So that means carbon's going to have 6 electrons. Now, carbon can lose and gain electrons. All the elements can lose and gain electrons. We say they form ions. Okay? But the number of protons is still the same. Okay? So that's important to realize. For instance, chlorine often gains an electron, forms the chloride ion Cl-1, right? Which is what you find in salt, sodium chloride. Okay? And they gain and lose electrons kind of like they want to be like these guys over here. Chlorine wants to have 1 extra electron to be like argon. That's what you typically see. Sodium loses 1 electron, and it'll be positively charged. So when you lose electrons, since it's negative, you become positively charged. You become a cation. If you gain an electron, which is negative, you become negatively charged, and you're an anion. And that's what happens when compounds form. That's what happens when you find them a lot of times in the body and in foods and in water. They're as ions, not as elements. Okay? But chlorine will still always have 17 protons. Carbon will always have 6 protons. Their number of neutrons and their number of electrons can vary. Okay? Now, what's interesting is the group often represents the charge which forms. So lithium, sodium, let's go back to sodium. This is common. You guys all know sodium, sodium chloride. These typically like to form +1. Sodium will be +1. Why? Well, it loses that electron, then it has 10, just like neon. I said to you, they kind of like to do that. If you learned a little bit of chemistry in high school, maybe you remember the noble gas configuration. We don't need to worry about that, the octet rule. But I want you to realize that group 1 is typically +1. Group 2 is +2. You get over here, +3. These guys don't lose or gain electrons much at all. These guys are going to be -1. These guys will be -2. And that's the general trend. So that's nice to know. And there's some things that vary in that. And you get to the middle of the periodic table, it breaks down. It's not as easy to figure out. But that's good to know. Good general knowledge. So if you see something like barium, Ba here, it's typically going to be 2+ if you find it in water, food, in a compound. So that's what's important. So a lot of you might take calcium as a supplement, as a vitamin, a mineral, something like that. That's going to be calcium 2+, and it might be as a form. If you look at your vitamins, it might say calcium carbonate. Okay, it's going to be calcium 2+ bound to something else in a compound. Just the way sodium chloride is sodium +1 bound to chlorine -1. So those are charges and ions that we see in nature and in compounds and foods. We talked about the atomic mass, which is simply that average mass of all the isotopes. We said isotopes are atoms of the same element with different numbers of neutrons. Okay? Now, one thing that's also interesting is when you get to the part on renewable energy, I will talk about photocells, solar cells. They're made a lot of silicon. Okay? And the valence electrons are the electrons in the most outer shell. Okay, so what you have is the nucleus in the middle, okay? And then you have orbitals of electrons outside that, multiple layers. The outermost layer is the number of valence electrons. That's what we call the valence shell. And it's kind of equal to the group number over here, 1 and 2, and the group number -10 over here. So it'd be 1, 2, 3, 4, 5, 6, 7, and 8. So silicon has 4 valence electrons, right? That'll be important later, that anything in this group here, the group are the vertical, the rows or periods are horizontal, the groups are the vertical. Families also sometimes called. Same number of valence electrons. So all of these here have the same number of valence electrons. All these here have the same number. So everything in group 14 has 4 valence electrons. Everything in group 13 has 3 valence electrons. Everything in group 15 has 5 valence electrons. That'll become important in the renewable energy section when you talk about solar cells. Those are the valence electrons, the outer shell. The total electrons for silicon will be 14, right? You see that? Same number, same as the number of protons. It's neutral. 4 valence electrons. Just tell you that there's 10 electrons on the interior of that valence shell. And the valence shell is important because that's the part that reacts. When two atoms come together, think about it. The two outermost shells are what react. When sodium loses an electron, guess where it goes? It goes to the valence shell. It loses it from the valence shell, and it goes to the valence shell of the chlorine, and you form sodium cation, chlorine anion, and they come together, opposites attract. Positive attracts negative. That's how the sodium chloride crystal compound is formed. Okay? And the last thing really I want to talk about in this video is radioactivity. And that'll be in your non-renewable energy section. So some isotopes are radioactive. Radioactivity is simply the spontaneous disintegration of the nucleus. Think about the nucleus. It's got a bunch of positive charges, protons packed together, and the nucleus is incredibly dense. It's one of the most densest substances in the universe. There's not a lot of mass there because it's really small, but the amount of mass in the volume is so small, it makes it incredibly dense. The only thing that's comparable to it is like a collapsed star. That's how dense this material is. So, a bunch of protons, which are positively charges, like charges repel, right? So you expect the nucleus to fly apart. The neutrons act to kind of help the nucleus stay together. It's called the strong nuclear force. Okay, but sometimes the combinations of protons and neutrons are such that the nucleus it can't stabilize itself. We say it's radioactive, it spontaneously decays. So carbon-14, one of the isotopes of carbon, is radioactive. Carbon-12 is not. So there's tons of isotopes. Every element has an isotope. And some have multiple isotopes. Many isotopes are radioactive, many are not. It just depends on those combinations. But what I'm getting at here is once you get down here, I'm on the periodic table, if you look at my mouse here, once you get beyond 83, get to 84, every isotope of every element beyond from 84 and beyond is radioactive, which means if I come down here to uranium, you all should know uranium, it's famous for nuclear energy. You'll learn about it in that section. 92, since it's greater than 83, all of its isotopes are radioactive. Doesn't matter. Where up here, carbon, only some of the isotopes are radioactive. So once you get to 84, all the isotopes of all the elements, that means 84, 86, 87, 88 come in here, 89, down here, all of these, 103, and then all of these. All those are radioactive. That's important. You should also know that once you get beyond uranium, these elements are pretty much do not occur naturally, and they're synthetic. So we synthesize them, and some of them have some uses. Americium is actually used in smoke detectors. But everything beyond uranium really doesn't occur naturally, except for maybe plutonium in minute quantities. But anything with usable plutonium is because we've synthesized it. Okay, so anything 84 and above, everything's radioactive. If it's less than 84, then it depends on that particular isotope. And that is really all I think I want to say about the periodic table. This is the same periodic table, one of the ones I've given you in your content section. And it's a nice coded periodic table. It's pretty up to date, so it's a good one for you to use. With that, I'm going to stop my video and use this throughout the semester as a resource. Stop my share, and now I'll stop the video.